Thanks for coming for the first meeting of our Warsaw Quantum Computing Group. So the first inaugural lecture will be given by Rafał Demkowicz-Dobrzański, Introduction to Quantum Computing, but yeah. Yes, but before Rafał starts, I will say a few words about the story behind this group, so why we meet today. A few months ago, I was in London attending similar meetup, London Quantum Computing meetup. The title of the lecture was Quantum Computing Takes Flight at D-Wave. And I had interesting discussion with people organizing this group and came up with the idea that it may be good to organize something similar in Warsaw and potentially collaborate, exchange lectures. So yeah, they will be one of our collaborators. But after coming back to Warsaw, I talked to some other people. So Rafał, for example, from Faculty of Physics, with Professor Mankiewicz as well, from Polish Academy of Sciences, Mateusz, also from University of Warsaw, and a few other colleagues. And yeah, we decided that it may be good to make it happen. And that's why we meet today. There are also some other companies which already supported us, or at least declared that they would like to support this initiative. So it's very likely that one of our next meetings will be hosted by Google, in Google Campus. We also had discussions with regard to quantum computing companies, so they are keen to also share some learning materials with us, so we can learn how to use their quantum computing platform, how to develop quantum programs which can be run on their platform. Yeah, so the goals, so there are three major goals of this group. The first goal is education. So as you know, or at least maybe you heard that the area of quantum computing has recently encountered very good progress. So there are major, very important announcements that given by some companies that they were able to build larger quantum computers than we had a few years ago. And some companies also released programming frameworks which allow us to just develop quantum programs and run them on quantum computing platforms. But also we learned that there are many people interested in quantum computing here in Warsaw or in general in Poland, so we would like to integrate our community. And in the future, perhaps we can also start doing advanced research in topics related to quantum computing, probably especially in applications of quantum computing in artificial intelligence, machine learning. So the idea is to meet once per month, at least at the beginning, usually Mondays or Thursdays at 6 p.m. How do you think which day of week might be better? Monday as today? Monday, okay, good. So let's try Monday. Initially we plan to organize the first meeting on 12th November, so exactly 1 week earlier. But as you know, this day was announced to be a holiday, national holiday. So we decided to move this meeting to the next week. So that's why we meet today. But anyway, we also wanted to celebrate the 100th anniversary of regaining independence by Poland. That's one of the reasons why we wanted to organize this first meeting on 12th November, and also that we organize it today. So today we meet at the Faculty of Mathematics, Informatics and Mechanics of the University of Warsaw. But we also had discussion with people from Google and also from Przestrzeń from Facebook. And it's very likely that our next meetings will be hosted by Google and also by Facebook. Maybe some of them will be also on the Faculty of Physics, we'll see. Our first meeting will be given by Rafał, so there will be only one speaker per meeting. But we also have plans to later have 2 speakers per meeting. So probably lectures, talks will be a bit shorter, maybe not 60 minutes. But maybe 45 or 30 minutes plus discussion. And the default language is English. So I know from the registration list that there are also people from so who are not Polish speakers would like to attend our meetings as well. So we are planning to record our meetings and then publish video on YouTube. So we already have our YouTube channel, and yeah, we are also testing live streaming on using Google Hangouts on Air and our YouTube channel. We have a Facebook group. There are more than 160 people right now. There are even 170, in fact. There was also idea to create a mailing list. So if you agree that that's a good idea, then probably I will do it and send you invitation. So probably that will be Google Groups mailing list. Okay, so today we have introduction to quantum computing. The next meeting will be probably given by Piotr or maybe another person from his team. It will be introduction to programming quantum computers. Next month in December, so the exact date will be confirmed, but initially the tentative date is 17th of December. And later in January and February there will be two meetings dedicated to Forest programming language from Rigetti. Yeah, it will be given probably by Michał Stękły. And you can see some other possible topics for the next semester, next year. Yeah, so, but if you also have your own ideas, maybe you would like to become a speaker, or you have some wishes that we should invite someone to give interesting lecture, then of course feel free to tell us, and we can adjust our agenda. All right, so thanks for your attention, and now Rafał, the floor is yours.
Okay, thanks a lot. So I'm Rafał Dobrzański, and I work across the street at the Faculty of Physics. So I want to give today introductory talk, so that somebody who doesn't know anything about quantum computing can learn something, and also people who know something will not be bored too much. So let me start by saying what is easy and difficult computation, because this is basically where quantum computing can show some advantage over classical computing, and to understand how you should first define what is difficult, what is easy to compute. So addition is easy because the number of operations is proportional to number of digits. So if you want to add two numbers with 5 digits, you perform operations which are proportional to the number of digits. So this is linear scaling of complexity of your task. So this is easy. If you multiply, then what is the complexity?
Linear.
The number of digits? It's linear?
Yeah, right. Yeah.
I don't know. If you do it at school, it's not linear, because you have to first multiply each digit by all others and then add. So it's like n squared operations. Yes. You take one digit, multiply by everyone, and then second, and multiply by everyone, and then add. So it's n squared. Maybe you can do it in a more clever way. Maybe people from this faculty know how to do it better, but okay. At school we do it like this, and at the Faculty of Physics we also do it like this. So, but still it's easy task, because it scales quadratically with number of digits, so it's not so bad. Okay, so now if you ask another problem of factoring, so if you have this number, you want to find its factors or prime factors, it appears that this is a difficult task, and the best classical algorithm scales approximately like this. I'm sorry if it's not a very rigorous statement, but the point is that the scaling is faster than any polynomial scaling. So any fixed scale you put here, this scaling will surpass this polynomial scaling for any fixed scale. And it's also slower than exponential. Okay, so it's super polynomial, sub exponential scaling for the best classical algorithm to factor numbers. So this is regarded as a hard task because it's super polynomial scaling in number of digits. So for example, if you plot it, like the number of digits in a number you want to multiply or factor, and then number of operations you need to perform to do it, then you see that initially maybe the difference is not so huge, but later on it's tremendous, because this is logarithmic scale here. And for example, if you had a supercomputer operating from the beginning of the universe, you would be able to compute this. You would be able to have this number of operations performed. So, I mean, digits here is in terms of decimal systems. Okay. So probably you know that this is good, that factoring is difficult, because this is the basis of public crypto systems that all of us use. And if factoring was easy, we would not feel secure when we see HTTPS symbol. And, okay. So formally, and I understand that at this faculty you probably see such things like Turing machines and complexity classes. So you formalize all algorithms, at least all classical algorithms, you formalize in a way that you say, that you ask how many operations are required, how many elementary operations are required to perform on so-called Turing machine, okay, which is like a paradigmatic computer, classical computer. And then you define different complexity classes for algorithms. So in particular, P are algorithms which you can solve in polynomial time. So for example, multiplication or addition. NP are the problems that you can check if the solution is correct in polynomial time. Okay, and then there are different classes where you need polynomial space, but time may be not polynomial. And then you need exponential space, exponential time, and finally you have this class of undecidable problems which are related to the stop problem. And as you can see, there are all question marks here. So nothing is really known in complexity theory, as far as I understand. But now, if you want to see how quantum physics enter into this picture, we would need to define a new complexity class. That's complexity class that is can be efficiently run on a quantum computer, but not on a classical computer. And the question is where this complexity class will be placed here. Okay? Because this will determine whether quantum computers are useful for something. So until physicists came into computing field, I mean, computer scientists and mathematicians were doing all the job. But essentially, computing is a physical process. So that's why physicists have something to say. So I will first mention a result which is not really very much related to our talk today. But this is actually a first important example where people realize that you should think about physics of your computing device, because it may be important for how well these devices perform. So there is this famous Landauer principle, which was formulated in 1960, which tells you that if you perform irreversible operations, so for example, if you have an AND gate, like here, yes, which has 2 bits at the input and 1 bit at the output, you have this logic table here, and you see that while you have 2 bits at the input, the output is only single bit, so this operation is irreversible. You cannot, in general, recover the inputs from the output. Okay? And this means that, by Landauer principle, such an operation requires is intimately related with some heat generation. Okay? So you can think about it in the following way, that if I have such a system and I want to compute this elementary gate will emit kT, where K is the Boltzmann constant and T is the temperature in absolute in kelvins heat. So it also means that you need to provide power for your computer. So if you know how much elementary operations your computer performs, then you can calculate what is the minimal amount of power it requires to be running. Okay. In fact, even present-day classical computers are not yet limited by this bound, because there are still much more imperfections that result in larger heat production. But maybe one day this principle will be relevant for classical computers. Okay? So actually there's not really much quantum here, but it's like when physics enters computing, and it may be relevant. But now we go one step further and we realize that the world is quantum, so we would like to think about computing from this quantum perspective. Okay? And this was already envisioned in a famous lecture by Feynman, where he said, there is plenty of room at the bottom, nothing that I can see in the physical laws says that computer elements cannot be made enormously smaller than they are now. And indeed he was right. And then he later on envisioned that what we would call quantum computer now. Now we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. The ones move around, the zeros move around. Finally, along a particular bunch of atoms, 1 and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant. So this is kind of prediction of what quantum computer might be, even though it's not really rigorously probably what we would today call a quantum computer. But the essential point is that we want to restore information in elementary quantum systems and manipulate them using laws of quantum physics. Okay? So when the quantum computer will appear on our desks, so there is this famous Moore law, which I'm not sure holds still, but assuming it holds, it tells us that approximately every 2 years the density of elementary electronical elements in integrated circuits, they reduce their size by 1.5 or something like this. So this is basically like exponential reduction in size over time of electronic devices. So you can now ask, okay, if this tendency goes on, in which year we would arrive at a situation in a single transistor is of the size of the atom. So that's how we can predict when real quantum computers should appear, and it can be extrapolated, this dependence, and then you realize that it will be like in 20 or 20 years maybe. So if it does not happen, then it means that the Moore law will not be valid anymore. Or if it is valid, then we will have a computer that operates on single atoms. So this will be like hopefully quantum computing. But still, it's not a sufficient requirement. We might say it's a necessary requirement to be able to control single atoms. Maybe it's not necessary, but anyway. It's not sufficient. So even if you can manipulate single atoms, it does not mean you have quantum computer. Because for quantum computer you need something more. You need to really be able to think about this elementary bit as a qubit. Okay? So as a quantum bit. And the quantum bit means that you not only are able to store zeros and ones in it, but you are able to store arbitrary quantum superpositions. So states in which you have, like in atom, you have ground and excited states, an atom in a ground and excited state simultaneously. So it's in kind of smeared state, which is a bit in a ground and a bit in excited. Or if you think about photons, you can think about a photon which goes one path and the other at the same time. Or you can say it goes neither of the paths, but it's in some weird state which is a superposition of these two paths. So why this will be a significant advantage to have such a superposition? So the main idea behind quantum computing is the so-called quantum parallelism. So you can now think that you have n qubits. So each of these lines, it represents a single qubit. Okay? And you can perform quantum gates on these qubits. So the quantum gates are generalization of classical logical gates in a way that they are able to operate on superpositions. But they are very similar to classical gates. If you write how they act on like zeros and ones, they look almost the same, but they additionally need to have this property that they are able to act on superpositions. So we have some quantum logical circuits, okay, which you can plot, for example, like this. And then, what is quantum parallelism? Quantum parallelism is the fact that you can prepare your initial state in a superposition of, for example, of all n-digit numbers. So instead of filling your device with a single set of zeros and ones, you prepare full superposition of all 2 to the power n numbers. Okay, and then you send it through these gates. And actually, quantum mechanics is a theory where evolution of quantum systems is linear, and it means that if you define some operation u, in quantum mechanics it's always a unitary operation, if it's ideal system. Then if its u acts on some basis state in some way, then on a superposition it will just act as a linear operator. So if you feed in superposition of all this initial data, at the output you will have a superposition of all the answers, for the outcomes of this computation. Okay? So this U encodes some computation process, and thanks to the fact that you can use superpositions, you can basically compute this problem for all initial data, for exponentially many initial data in one step. And this is called quantum parallelism. Okay? So it looks great, but there is a problem. We can write such things on paper or on a slide, but the question in real life is how to now read out these results, okay, of our computation. Because this is the state we would like to know the answer. So we would like to learn what are all of these output states. But in fact, what in quantum mechanics we can do, if we are given a single copy of a quantum system, we can only measure it once. And if we measure it, we have to define in what basis we measure it. So formally, these objects, they are vectors in a Hilbert space. And by saying that we perform a measurement, we define some orthonormal basis in this Hilbert space. And what we can do, we can project this state on some orthonormal basis and see on which vector it was projected, and what we can predict is only to say with what probability it will be projected on each of these vectors, and in the end we read out that the state is this. Okay? It was projected on something. So it is far less than just looking, just seeing all these output vectors here. And that's the real problem of quantum computing. That, essentially you see that it's there. Okay? It's a really powerful thing. But you have now to design algorithms in a way that, indeed, they require parallel computation, but not in a trivial way. So in the end, they should not amount just to the statement, okay, I want to read out all these results. They should require something which is a much subtle function of these results. Okay? Some kind of relation between these results. And if you are able to construct such an algorithm, then maybe you can benefit from quantum computing. But it's highly non-trivial. Okay? So the first idea was given by Deutsch, how to do it. And this is the simplest quantum algorithm. And in its standard version, it's the problem like this. That you have a function, a single bit function. So it's given a bit and outputs a bit. And you ask, what do you ask? You ask whether there should be inequality here. So you ask whether this function is constant, so it gives the same output for each input, or is it it has different outputs for different inputs. Okay. So now classically, if you wanted to learn which of these cases take place, what should you do? You should calculate f as a function of 0 and f as a function of 1. Okay? So we need 2 times, to compute it 2 times, this function. There's no other way to learn. Just please remember, this is inequality here. So now we ask, can we do better with using quantum computing ideas? So first we have to define a quantum gate which will implement this calculation of this function. So we will define a gate which acting on a vector which can be like 0 or 1 vector, so 2 basis vectors, we have 2 basis vectors, 0 and 1. And we define a unitary operation that depends on this function f in such a way that it produces this vector, but maybe it will be multiplied by -1 or by +1, depending whether the function is 1 or 0. Okay? So this is the way we implement this classical function into a quantum operation on vectors. They just multiply this vector by -1 or +1. Okay, and now we prepare our input qubit in a superposition of 0 and 1. And we act with this gate. And then by this linearity of evolution, we see that it acts on 0 and gives us -1 to the power f of 0, and then -1 to the power f of 1 gives us the vector 1. Okay? So this is just a single computation here. We just use this gate once. And now we want to see that it's enough. Okay? So contrary to classical problem where we need to use it 2 times, here we will only use it once. So why? Because now you see that depending on this, whether it's this case or this case, so you see if we have f equals 0, f of 0 equals f of 1, it means that these exponents here are the same. So this means that this output state is 0 plus 1 with plus or minus sign in front. Okay? So formally you could draw it in your vector space as such. So these are the spaces vector 0 and 1, and here it's 0 plus 1. Okay? This vector and minus 0 plus 1 will be the vector pointing the other way. Now, if this is the second case, so if functions are different, you will get a relative sign between these two terms, which means you get 0 minus 1 with plus or minus. So then this vector is this one or this one. Actually, physically, yes.
And so there's a spelling on this slide.
There could be a lot of spellings, yeah? So here, yes?
Yeah.
Yeah, so then I mentioned it for the 5th time, so there should be inequality here, yes. But good that you asked, yes. I'm sorry. So, so there's inequality here all the time. So now you see that we produce two vectors which are orthogonal to each other. Okay? And now we can perform a quantum measurement exactly in this basis. So we take one basis vector to be 0 plus 1, the other basis vector to be 0 minus 1, and we project our state in this basis. And if we measure this state, we know that functions are identical for different input arguments. If we produce this state, we know that the functions are different, and this is this case, just using a single computation. Now there is some subtle thing. This plus minus stuff, which is in front of the vector, it has no physical meaning. Okay, so for physicists, this vector is physically equivalent to this vector. Okay, in quantum mechanics, multiplying your quantum state by a complex number of modulus 1 makes no difference to the physical content of this state. So that's why the fact that this is plus minus is really irrelevant. Okay? So are there any questions to this example? Because I think that if you want to understand something from quantum computing, this is something you can easily understand, and everything else is just generalization of this. This is the essence, this fact that you perform parallel computation, and then you do not ask for the results of these functions, but some relation between them. So like here, you only ask whether they are equal or different, and that's why there is no problem with this reading out all the results, which you cannot do simultaneously. You can read out only something, and this something must be something you really need. Okay? And that's a good quantum algorithm. Yes?
Is there any simple reason why multiplying your vector by plus minus 1 or any complex number doesn't matter?
So okay. So I can give different answers. So okay, in formalism of quantum mechanics, it's like this, that all you observe, all you can predict are probabilities. And probabilities are computed as modulus squared of scalar products of your vector with some basis vectors. And that's why this phase factor, they always cancel out, because there's the modulus squared of this scalar number. The other thing is, if you think more physically about it, and for example, think of light interference. Okay? Because like a model for quantum effects could be interfering light or photon traveling through two slits on the screen. So you send your light, it goes through two slits, and then it interferes on the screen. And now, depending on the position of the screen, you get either constructive or destructive interference. Now, in quantum language, if you want to describe such an interference effect, you would say that your photon is in superposition of going one hole and the other hole, and it somehow splits and then interferes on the screen. And then these two ways are the 0 and 1. So now if you say that I multiply phase of both of these paths, it physically it would mean that you increase the length of the path the photon has to travel, but in the same way in both of these holes. And this will not change interference pattern, because interference pattern only feels like relative phases between these two parts in the superposition. So if you want to think physically, you can always think about such terms as representing photon traveling two different paths, and then you perform some experiment where you interfere these paths. And multiplying both terms by the same phase physically means you just let it evolve for a longer path. So the same phase is being acquired for both of these terms, and interference picture does not change. But if you add now relative phase, so you just, for example, add minus here but no minus here, it changes the relative phase between them, and for example, in interference picture, you change from a bright spot to a dark spot.
So we can kind of think about this 0 as a pure 0 bit, about this 1 as a pure 1, and 0 plus 1 is a superposition of those two, right? Superposition of those two. Then how do we interpret this 0 minus 1? Because
it's also a superposition, but with different relative phase. So logically, you would still say that this is like equal probability of measuring 0 and equal probability of measuring 1. Okay? In both of these things. In this and this, from this point of view, there is no difference. So if you just ask whether my qubit is in 0 or 1, there is no difference between these two states. But you can now switch to different measurement bases. So that's what quantum theory gives you, that it gives you the whole space of all superpositions, and you may equally well say that I'm not measuring in 0 and 1 basis, I'm measuring in 0 plus 1, 0 minus 1 basis.
So the size of the space is 2 times the space of my qubit space, right? Always? Or?
Yes, so okay, the size of the whole space. Yes. Yes, because each qubit is a 2-dimensional system.
Yeah. Okay. A complex number, right?
Yeah, okay. So the amplitudes will be complex numbers. So
okay.
You always define Hilbert, you can define a Hilbert space by providing a basis. Okay? So basis for a single qubit is 0, 1. If I have n qubits, I have all combinations of zeros and ones, yes, all n-digit numbers. And I can write that these are my orthogonal vectors. Because I can measure in this basis, and I can explicitly say whether my state is this, or this. But in quantum language, I can also take arbitrary superpositions of these things. So it means that I operate in a vector space of dimension 2 to the power n. And I can have such states with arbitrary complex numbers in front. Okay, formally we always normalize vectors. So vectors are normalized to 1.
Yeah.
So the modulus squared of these numbers sum up to 1. And additionally, I can always say that the phase that multiplies everything is irrelevant. Okay, this is additional number which I can throw in.
Okay.
And then I have a full description of any qubit states.
Okay.
So any more questions? Yes?
Like I can imagine how to measure like a projection of this state on some, let's say, plane or on some vector, right? But how to measure simultaneously like on the whole base? I can't.
So
like
you ask how to measure in these different bases, yes?
What physical phenomena corresponds to such a measure?
To measure it in 0 plus 1?
Like
yes?
in this orthogonal basis, like let's say you have like 10-dimensional space, and how you measure all those dimensions.
Wait, but your question is about how to measure a single qubit in this strange basis, or how to measure this n qubits in this big space? Both questions, okay. Okay, so maybe first this one. So, of course it depends on physical implementation. So, for example, if you think, I don't know what's more appealing to you, whether it's the levels of atoms or photon traveling different paths. What do you prefer? What?
Levels.
Which one is better?
Levels of atoms.
Levels of atoms? Okay. So if these are atomic levels, then measuring in 0 and 1 could be like checking which energy eigenstate you are in. So it means measuring energy of your atom in some way, which may also not so obvious, but okay, let's assume this is easy. So now, if you want to measure in this basis, a physicist would usually, what a physicist would usually do, he will or she will let the system evolve for some time with a Hamiltonian that changes this basis to this basis. So you apply some additional unitary operation, which you can control, you know how it acts, which will change this basis to this basis, and then you measure using simple measurement you know. Okay? this is how it would usually be done. So you are right that this is not intuitive how to measure it directly. You usually measure it in effect by performing some additional operation that transfers you to the basis which is simple to measure in physical terms. Like, for example, with photons, it's easy to measure 0 and 1 because if you have these two paths, it just means I check whether the photon is here or here. Okay? I put a detector here or here. Now, if I want to check whether it's 0 plus 1 or 0 minus 1, I have to interfere these two paths first. And this will correspond, for example, on a beam splitter. So on a glass, which has like 50% transmission, 50% reflection, yes? I interfere it, and then I measure where photon went in the end, and this is actually exactly, this corresponds exactly to this additional operation on atom. So here my additional operation would be this beam splitter, which would transfer these superpositions to 0 or 1 at the output, so it will send my photon to either one arm or the other. Okay? It's okay? So any more questions? Okay, no more questions. Good. So this is the summary of the Deutsch algorithm. So the Deutsch algorithm is not very impressive because it just gives you a factor of 2 improvement, and for a problem which is not so interesting probably. But still it was the first example of an algorithm, and it's very simple to understand. And now there comes a much more interesting algorithm, the so-called Shor algorithm, which I will not describe in detail, maybe because it would require a whole lecture. But the Shor algorithm is an algorithm that allows you to factor numbers. So I mentioned in the beginning that factoring is a difficult problem, and if we could factor, we could steal a lot of money. And the Shor algorithm actually does it. So if you remember, classical computer complexity, it was super polynomial. Okay, so the complexity grew faster than any polynomial, n to the power of 100 or anything you want. Shor algorithm complexity is only n to the power third. So it's only a bit larger than multiplication. Okay? So it's extremely fast. So if we indeed had a quantum computer on which we could run this Shor algorithm, the world will be changed forever. So you see, if I add a plot here, it's like not far from this multiplication. So, so then everything will not be secure. So I just mentioned, as I said, I cannot explain it in details, but I will just mention that the essential element in the Shor algorithm is the so-called quantum Fourier transform. So if you know, Fourier transform is also a quite computationally consuming task on classical computers. And if you have, for example, let's say we have data which consists of 2 to the n. So, like you sample your music, yes? Because what's Fourier transform useful for? If you sample your music and you want to see the frequency profile of your music, okay, where is the more bass or trebles or something. So if you sample your music and you have 2 to the n samples, and you want to perform Fourier transform, then you will need 2 to the 2n elementary operations to do it. There is something called fast Fourier transform. This is a classical algorithm that reduces this 2 to the 2n to n to n. So it gives you 1, 2 to the n changes to n. So it's like exponentially fast, but still exponentially complex. While there is a quantum Fourier transform, so this unitary operation that you can implement using n squared gates. So it's exponentially faster than fast Fourier transform. Of course, it has this drawback that you cannot read out the result. Okay, as in classical algorithm, you could. But factoring problem can be, in an intelligent way, translated to the problem of performing Fourier transform without really the need to read out all the answers, but just try to read out some periods of certain functions. Okay? Because you can imagine that Fourier transform sometimes somehow detects frequencies very well. So indeed, in this case, this is the whole scheme of Shor algorithm in this sense. But the essential feature, and this is what gives you the speed up, is this block here, which is this quantum Fourier transform, QFT. And because of this, you get this exponential reduction in complexity. Yes.
Is it quantum Fourier transform or inverse quantum?
Yeah. Okay, it's the same. Inverse means it's inverse operation. Okay? Like unitary, you have a unitary matrix. You have inverse unitary matrix.
I have forgotten my knowledge about Fourier transform, but if you have quantum Fourier transform, can you inverse that result with non-quantum machine?
Can you invert what?
Can you reverse the result of quantum Fourier transform?
Yes.
You have done this calculation and you need to inverse it. Can you?
Can you invert it?
Just inverse function, can
yes.
you get just inverse function in polynomial time with non-quantum computing?
Okay, so maybe I should mention it in the beginning. Classical computation is usually done using irreversible gates. Yes, this is what I mentioned with this Landauer principle and all this stuff. You have these AND gates that take two bits to one, and it's irreversible. Quantum computing is almost always done using reversible schemes. So you always, in these plots, like I plot here, you always have the same number of qubits at the input, the same number of qubits at the output, typically. Sometimes you throw away some of them in the end, but when you compute things, you always keep all the qubits on the run. And as I mentioned, quantum mechanics operations are unitary. Unitary operations, mathematically, are always invertible. Okay? Because inverse of a unitary matrix is just its conjugate. So it's always invertible. It does not lose any information. So whole quantum computing is always done using reversible computation. You can always reverse it and go back until you measure. When you measure, you can no longer reverse it. Okay? Measurement is the point where you break this reversibility. Otherwise, everything is reversible. So I should stress it. So thanks for this comment. Of course, you can always also do classical computation using reversible circuits. But I think nobody does it. Maybe correct me if I'm wrong. Because it grows really complex in terms of the circuits and gates and so on. Of course, it has this advantage that in principle you would not have this Landauer heat limit. Okay? If you perform reversible computation, you are not limited by this necessary heat emission. But still, as I mentioned, at the moment it's not really a problem for present-day computers. And on the other hand, the complexity of these reversible circuits is much larger than reversible circuits. But in quantum mechanics, we have to do reversible, because usually if you do something irreversible, you destroy the superpositions, all of them. So we really don't want irreversibility in quantum mechanics until measurement.
But Landauer law applies to this final measurement.
Yes. I mean, if you lose information in the end, yes. You can also apply Landauer principle there. So typically, if you remove information, you always emit heat, and it doesn't matter whether it's classical or quantum system. So yes, Landauer principle is a very universal principle. Okay, so let's come back to this X. So where is this quantum algorithms in this picture? So complexity class related with quantum computing is usually the most popular name. Class is BQP, which means bounded error quantum polynomial time, which basically means that you can run quantum algorithm in polynomial time, and the error is bounded. So it's not like that. The error grows, and the probability of error grows to 1. Okay? When you run it. because then it would be like probabilistic machine which very rarely gives you the correct result. It has to give you like finite probability of good answer even if you go to the limit of large number of digits. Okay? So from this you see that there is some hope that some of NP problems could be within this BQP class. And so for example, factoring. Of course nobody proved anything, because no proofs are available in complexity theory, but this is what is expected, that this factoring is somewhere here. So now what are other quantum algorithms? So this is this Deutsch algorithm I mentioned before. We have this Shor algorithm, which indeed gives you exponential speedup, unless there is some unknown classical algorithm for factoring, which also gives you the same, which we don't know. It's usually like this. But we really cannot be sure whether quantum algorithm is faster because we don't know the bound for the best possible classical algorithm. Then there is Grover algorithm, which I put in gray because it gives you only quadratic speedup. The Grover algorithm allows you to search through unstructured database. So if you have typically you present it in a way that you want to, you have a telephone book, yes, and you want to find whose name is related with telephone number 6543210. So you have to browse through your telephone book to check where is this phone number. Okay, and it's unstructured because the telephone book is ordered by names and not by phone numbers. Okay, so that's why you need linearly, the time to find the entry you are interested in grows linearly with the number of elements in the database. And classically you cannot overcome this. While the Grover algorithm is a way that allows you to find this entry in square root, in time which grows a square root of number of elements. So it's interesting, but it's only quadratic improvement. And taking into account complexity of everything that's quantum, quadratic improvements are not so clearly advantageous over classical schemes. Okay? So that's why I put it in gray. Unlike Shor, where you have this exponential speedup, so even if you have to pay more, then the gains are also high. So then there are some other algorithms that people try to invent, because as you can imagine, I hope from what I said, it should be clear for you that it's very difficult to find a new quantum algorithm. Because you have to find this clever way to combine all the results to give you the answer for what you need, but you cannot just read out these results. You have to just play with them in a clever way. So there are also some algorithms related to deciding whether the graph is connected or not. But this also is only like quadratic game, similar to Grover. And recently there was a big news. Recently, it was 2 years ago, because it was found out that you could have an exponential speedup. Maybe you could have an exponential speedup in something which a lot of people would find extremely useful. So the so-called customer recommendation systems. So if you have this Amazon or Netflix companies, they store a lot of data concerning your choice or your choices. Yes? What movies did you like and what books did you read? And then they store it for you and all other people. So usually it's stored in a very huge matrix. So like there are people and there are these movies. Okay? And each person has only very few entries because nobody can watch all the movies. Yes? So this is a sparse matrix. It's a very sparse matrix. There are a lot of zeros there. But understanding the structure of this matrix can help you to advise a user what movie he should watch next to be most happy possible. Yes? So to enjoy it the most. And so this is this recommendation system that they give you a next book or next movie that you should watch because they see how well your choices are correlated with some choices of other people, and because there is some partial overlap, not complete, it allows them to guess what will be your next best shot. And mathematically, this problem is often translated to the problem of inverting this matrix to solving some linear equation. And of course this matrix is huge, and inverting it takes a lot of time. So people were thinking how we can improve it using maybe quantum algorithms. And actually there was a quantum algorithm that was shown that it maybe cannot invert this matrix, but it can produce you this sample that you really will like. So without really inverting it completely, it gives you the samples that you really want. So actually solving this problem. Just walking a bit around it, but solving it. And indeed, it was in this problem. It seemed that there is this exponential speedup, but actually in 2018, this summer, it was shown that you can find a classical algorithm that has the same complexity. But interestingly, this classical algorithm was really based on the quantum algorithm, because it used very similar ideas, but they just realized that you can translate it in a way that you really do not need this quantum stuff anymore.
Why do we, should we have exponential speedup if like inverting matrix is
because you don't actually invert,
yeah, but
and the complexity is logarithmic. It's logarithmic in this size. So in this sense it's exponential, because producing the samples is only logarithmic in the size of the matrix.
Okay, so I don't. Okay.
Of course, you could not invert in logarithmic time because there are more entries. Yes. but that's why this algorithm just gives you a sample. Okay? Of course, this matrix has to be stored somewhere, but provided it's stored in something where you can access it in a quantum way, it only requires logarithmic number of operations to produce a next sample for the user that comes. But as I say, unfortunately, it's not now an example that you can show. And I understand that people here at the Faculty of Mathematics are excited about these generalizations of machine learning algorithms to quantum machine learning algorithms. And so in some sense this problem is an example of this general class of algorithms. And a lot of people work on this, but I'm afraid I'm not able to give you like a concrete example where I could say that yes, this is like quantum speedup here. But we have some experts here who maybe might tell us something more. Okay, I think I'm running short of time. No, okay, still a few minutes. When you talk about quantum computing and you have some clever people in the audience, then sometimes such a question appears. So you are talking about the superpositions and all this stuff, but basically we know that you have also superpositions in classical physics, like waves. You can consider superposition of classical waves, like waves on the water. And formally it looks very similar to what I'm talking about. So like this superposition of 0 plus 1. Okay, you can say that this wave is 0, this wave with different frequency is 1. I take this wave and this wave simultaneously, okay? And I have this paddle waving, okay? And this is my qubit. And it's formally okay to say something like this. But then you could ask, okay, so where this quantum advantage comes from? And this is actually the question about what's the difference between quantum computing and analog computers. Because such a wave thing that you use to compute could be a version of analog computer. Because there is nothing discrete there, nothing is discretized, everything is continuous. And actually this is the reason. That we have, of course, superpositions and all this stuff, but in quantum theory we have more. We have discrete results, and thanks to this we can also think about errors in our system as being discretized. So actually, if you thought about waves and water and you wanted to perform much more demanding computation, so encode more digits in your waves, okay? You would need to use more frequencies and more frequencies, okay? More of these waves. Actually, number of frequencies would grow exponentially with the number of digits. And you may imagine that if everything is continuous and analog, there is no discretization, the noise will kill you. Okay? At some point, everything will be smeared out and you could not read out anything efficiently. But in quantum theory, it's different because everything is in some sense continuous in the sense of these waves and superpositions, but still measurements are discrete and you project on a basis, and also you can discretize errors. And this is the key point I want to mention, which is the reason why quantum computing makes sense at all from a physical perspective. Because you could invent quantum algorithms or all this stuff, but if you did not know how to do quantum error correction, nothing would work in practice. Because even if you build a very good gate in a physical system, there always will be errors. Okay? Like in classical systems. In this computer you also have classical error correcting codes to keep your memory, do not lose information, to keep your storage device, to protect information and so on. Because, for example, let's say I have a gate which acts well 99% of the time, but 1% of the time it fails. Okay? And now, let's say I run Shor algorithm with, I don't know, thousands of gates and so on. If each gate fails 1%, with 1% probability, and I have like 100,000 gates, then the probability that all of them succeeds, okay, it's like 99% to the power of 100,000 or something, so it's 0. Okay? So there's no chance I will succeed to calculate anything. So I need to have a theory and methods to do quantum error correction to really be able to make these errors as low as possible, even if my elements are faulty. Okay, so this is the idea. And okay. So the idea is that we need to have a method to protect this superposition. So imagine the simplest situation. Okay, I'm not sure how much you will allow me to speak here, but just in case I stop. So imagine you have this superposition, and let's assume we have a very simple error. For the moment, assume the only error that can happen is a bit flip, which means that 0 goes to 1 and 1 goes to 0. This means that with probability p, this state psi goes to alpha 1 plus beta 0. Okay. If we did nothing, in quantum language it would mean that instead of pure state we had before, we have something called mixed state, which is a noisy representation of a quantum state, where with probability p we have this state, and with probability 1 minus 2 we have this state. Okay. But now you can use an error correcting code. Error correcting code in this case will be something like this, that you have this logical qubit here, and you encode it into 3 physical qubits. Okay? This is like the simplest error correcting code that you know from classical error correcting codes, if you know them. So you simply encode it like this. Now, if you assume that level of errors is low enough that at most 1 bit flips, it means that either no error happens and you are still left with this state, or error happens on qubit 1, then you have this state, or error happens on qubit 2, you have this state, or error happens on qubit 3, you have this state. Okay? Now what's nice about it? Even though you don't know alpha and beta, so you don't assume you know this superposition, it's arbitrary superposition, you should now see that this state lives in orthogonal subspace to this state, and to orthogonal subspace to this state and to this state. So all of these cases, they live in orthogonal subspaces because they have different base vectors in this superposition. Which means that in principle you can perform a measurement which just tells you in which subspace you are. It's like projection measurement, but not projecting you on a given vector, but on subspaces. Like you could say that it's kind of weaker measurement than typically. Okay, we would call it like coarse-grained measurement. So a measurement which just projects you on subspaces, and gives you an information which subspace you are in. And then, if you know you are in this subspace, you do nothing. If you know you are in this subspace, you additionally perform again another bit flip on the first bit to go from this state back to the original state. Okay? Without actually measuring which of these two states you are in, because this would destroy superposition. So you don't measure which state of these two you are in, you just measure which subspace, either this subspace or this subspace or this. And thanks to this, you measure, you detect error, and you correct it, preserving superposition. Okay? And that's a great idea, but now you have to believe me that what I described here with just a simple error, which is a bit flip, actually works for arbitrary errors. And the reason for this is that you can discretize them, and this code would not work for arbitrary errors, but a code involving 9 qubits, or 7, or maybe 5, would work. So you have to make a more sophisticated code to be able to correct for other errors that can happen to a qubit. But you can do it. And you can again have a protocol where you project on subspaces and correct errors and keep your superposition alive.
So we do not collapse if we check in which subspace we are. But we would collapse if we measure what? Alpha and beta, right?
Yes. So you would collapse if you measure it in this state lives in 8-dimensional space.
Yes.
Because you have 3 qubits, 2 to the n state. And if you performed a measurement which would tell you which of these 8 states you are in, you would destroy everything. So instead, you have to be clever and perform a measurement that gives you less information. It just tells you whether this is it, this space, 2-dimensional space, whether this is this 2-dimensional space, and so on. Of course, you have to know how to do it, but it's not that complicated.
Okay.
You have to again perform some operations that, for example, only feel some kind of parity of bits or something. Okay. So I'm finishing soon. So what I described here is the standard approach to quantum computing. You have gates like in classical computing, so you have quantum gates in quantum computing. And there is a nice theorem that actually you don't need so many different gates to build a universal quantum circuit. Like in classical circuits, you just need NAND, one logical gate, to build arbitrary logical circuit. In quantum computing, what you need is one gate which would act on 2 qubits, for example, so-called CNOT gate, which is like quantum generalization of XOR, okay, so it's controlled NOT gate, and then single qubit operations, so operations that would operate in a single qubit without interacting with others. So single qubit gates are usually very easy to implement in physical systems. You just, for example, for photon, you just use these beam splitters, delay lines. For atom, you just send some light pulse on your atom to prepare superposition of two levels of this atom. The difficult thing is to perform this controlled NOT gate, which is kind of gate that involves 2 qubits, so 2 atoms or 2 photons, and they have to interact with each other in some way, okay, to perform this gate. This is like, this gate requires interaction between 2 qubits. And if one had this gate, and could combine them with others, then the quantum computer will be built, because we know how to do quantum error correcting code, so we will build these quantum error correcting codes from these gates, even if they are imperfect, and then we know how to run Shor algorithm. So if we had like, I don't know, 100,000 gates with 99% fidelity, probably Shor algorithm could be run and break the present day crypto systems. Okay, so this is just a CNOT gate, this logic table. So indeed, so we would have quantum computer provided we can satisfy these constraints. So we have to be able to preserve superposition, to have high fidelity gates, so gates with low noise, but not perfect gates, because this quantum error correction will help us. and we need to combine them in bigger systems. Yes?
So if you have n qubits, and you make them interact with each other with those synod gates.
Yes.
Two qubit synod gates.
Yes.
But you can argue.
Yeah, you can connect them in different ways.
Okay, so
and you can prove that arbitrary unitary operation on n qubits can be decomposed into single qubit unitary gates and 2 qubit synod gates. And in this way, and this is essential to count complexity of quantum algorithms, because to say something about complexity, you need to define what is your elementary operation. Okay? So for example, in quantum computing community, you define, okay, the number of single qubit gates and synod gates tells you what is the complexity, so how it grows with the size of the problem. Okay? So this is like standard approach to quantum computing. This is something people started with and developed still. But there are some alternative approaches to quantum computing which formally are equivalent, but maybe they have some advantages. So this is a very physical way to approach a computing problem. It's called adiabatic quantum computing. So the basic idea is such that you have a quantum system with a lot of particles which interact in some way, and you can prepare them in some initial state, okay? And that's easy to prepare. So you can prepare them in some state which is a ground state of some simple Hamiltonian. So Hamiltonian describes the physics of your system. Yes? How elements interact, what are the energies. So this is your starting point. And then you cleverly think of another Hamiltonian for which the ground state of this qubit is a solution to your problem. Okay? So of course it requires a lot of thinking. So which Hamiltonian will have a ground state which is a solution to some problem I want to solve. Okay? But once you have it, then you can run so-called adiabatic evolution, which means you tune your knobs in your laboratory in a way that your initial Hamiltonian is gradually changed to this final Hamiltonian. So this S parameter here goes from 0 to 1. Okay, but slowly. And there is something called adiabatic theorem in quantum physics, which tells you that if you run this transition slowly enough, your ground state will remain the ground state of the final Hamiltonian. So if you change this S slowly enough, you start with ground state of HI and you will end up in a ground state of this HF. And then you read out your result, and this is the solution. And this is actually how the D-wave operates. Okay, if you heard about this company in Canada, which apparently they build quantum computers, which they do not, but what they do is they build quantum adiabatic machines, okay, you could say. So the machines that do this thing. And the problem here is this statement slow enough. Because if you now want to prove some quantum advantage, you have to show that you are faster than any classical algorithm. And unfortunately, what they do is just they build this device and say, okay, let's do this and see what happens, okay? And they compute something and they show, okay, that's nice, but then a few months later, some people say, okay, we did it on classical computer, we just implemented this algorithm in a different way and we obtained the same speed up. Okay? So there is no quantum advantage. And actually, you should not expect a big quantum advantage from this D-wave system because it's very noisy. So even though in principle this idea is good, and you can prove that it's equivalent to this circuit-based quantum computing, the essential thing is how the noise affects the speed with which you can go through these adiabatic transitions. And this is what physicists say, that if you analyze this D-wave, you will see that this speed is slow and you cannot get this improvement over classical computation. Now, I think I wanted to say something here. I forgot. Okay. Okay, so now just to give you other ideas. So more conventional way to approach quantum computing is using so-called ion traps, where you really have single ions and you perform quantum gates on them, and you address each individual ion and you allow them interact like by pairs, performing these CNOT gates and so on, by making use of the fact that they oscillate together in a common trap, like electromagnetic trap. You have also an ideas where you try to perform quantum computing just using photons, which at first sight seems to be impossible because photons do not interact. And I said that CNOT gate requires interactions. Photons just do not interact, they just pass each other, okay? They don't see each other. But if you are clever, you can combine this interference of photons with some single photon detection schemes, which can conditionally produce transformations that you need for quantum computing. So again, I cannot explain it in details, but there is a way to build like fully optical quantum computer as well. And there are these ideas based on superconducting devices where you make use of the fact that superconductivity is one of very few phenomena which is quantum but still macroscopic. So you really can have big current in a superconducting circuit, but the basis of superconductivity is really very quantum phenomena. And in this way, you can make qubits which are not extremely small. Okay? So you can make qubits where you have these electronic circuits which are of the size of typical electronic circuits, and you can play with them and prepare like superposition of current flowing one way or the other, or electric charge being here or there, okay? And it's really a qubit. And this is actually the way that most of the companies like IBM, Google and Microsoft are pursuing, and what they build, like this 50 or something quantum computing device. And actually D-Wave also uses this superconducting qubits, but as I mentioned, D-Wave uses it in a completely different architecture, so in this adiabatic approach. While these companies are really building like more typical quantum computer where you perform gates and so on. Okay, this is D-Wave. Okay, so okay, I'll skip this. So I just finished with the last slide. So I just give this last slide saying that apart from quantum computing, which we may expect will make some progress in the near future, so in principle we can expect like 100 qubit quantum devices, but these are like noisy quantum computers still. So they will not have implemented this quantum error correction idea, because this quantum error correction idea requires like significant overhead in number of qubits. So maybe in the next year or two we will have like a noisy 100 qubit quantum computer, or maybe within this framework a 2 qubit quantum error corrected device. So like that really we perform true quantum error correction and can preserve few logical qubits for very long times. Okay? So, but I just want to mention something which is a bit closer to my heart, that apart from quantum computing you have other ideas in quantum technologies, like quantum metrology, which is a way to, again, exploit quantum superpositions in a clever way, but to measure something better than just using photons or atoms in a typical way. And there is a spectacular experiment, as you know, gravitational wave detection in LIGO. And actually, this year, they are implementing so-called squeezed light in this LIGO device, which means that instead of standard laser light, they send in something which can be viewed as light where there are entangled photons. So photons with some non-trivial correlations between them. So this is actually what I usually think about quantum metrology. So this is the protocols where you benefit from quantum entanglement, so from something which is not present in any classical theory. And this is actually happening, so it's not like fiction, it's being done, and it will give you reduction in noise which you can observe. So this is like real quantum technology in real life. It's being implemented now. The other thing that it's really being implemented now is this quantum communication idea. So quantum cryptography, for example. So how to distribute keys securely, knowing that nobody eavesdropped on us. Okay, so how to distribute the key. And probably most of you heard about this Chinese satellite that beat the record of the distance to like a few thousand kilometers, distributing entangled pair of photons and in this way distributing secret key. Okay, sorry for making it longer, but I hope you enjoyed it. Thank you.
Questions for Rafał?
Oh, I'm sorry, it was too...
Okay, so I have one question. Can I ask? Okay. So you said that we can prove that this universal or standard approach to quantum computing is equivalent to adiabatic approach. But can we say something about time complexity of algorithms? You said about this time of this example.
Yeah, so if you have noiseless protocols, then you can show that it will be the same complexity. But the problem is what happens if you have noise. So in standard computing, it's very easy. I mean, it's known how to quantify, how to deal with noise, because we have these quantum error correction ideas, and we know how much more gates we need to sacrifice to reduce errors and still have this complexity gain. While in this adiabatic approach, you just play some heuristic arguments, and you really cannot predict well how fast you can go in such and such noise levels. So that's the problem, to just guess.
Are we limited to linear operations in quantum computers?
Yes.
Okay, so only linear.
Yes.
In some sense. So if we...
even unitary, yes. I mean, unitary plus measurements.
Yeah. Okay. Okay.
So, of course, you could think of nonlinear evolutions and it will change a lot, but...
And the reason why, for example, this Shor algorithm haven't broken the anything yet is like how many qubits would it require actually?
Yeah, so as I said, I mean, probably if you wanted to have like this, so you need like, what is RSA uses 4,000 bits, I think, RSA key. So to run Shor algorithm, you need roughly twice as many logical qubits as the number you want to factor. So let's say you need 10,000 logical qubits. Now, if you want to have a logical qubit, you need to have like maybe 100 physical qubits to encode this error correction, quantum error correction. Okay? So 100,000, I guess.
Okay.
Physical qubits with like fidelity, with high fidelity.
And is there any physical barrier like we showed in case of classical CPU for like development of these quantum computers?
So the law that would prevent us from building quantum computers. So some people claim there is, but we don't know it.
Okay.
So some people try to argue that quantum computing is nice, but there is some fourth or fifth law of thermodynamics that forbids it. Okay. Because on one hand you have to isolate your system, but on the other hand you need to let them interact with each other to perform this gate. So maybe there is this compromise that you cannot beat, but this is just speculation. And most people would believe that it's only engineering code.
Okay. Questions?
So you said that the errors that occur in this huge sequence of gates may grow with the amounts of gates.
Yes.
And still, this error correction works in arbitrary size of the system.
Yes. Yes, that's true. Because maybe this is what a question or you want to
Yes,
answer?
that's what question.
Yeah, but okay, so for example, I can factor a number with 100 digits, okay? And I do it with some small error. Now I want to factor a number with 1000 digits, okay? Which means number of my logical qubits increases n to the power 3. And of course I have more gates. And before I had some probability of error. Okay, so now if I increase this protocol longer and longer, these errors may grow not nicely. So now I need to enlarge my error correcting codes to reduce error of a single logical gate significantly enough. So now you have to ask the question, does the growth in the quantum error correction size does not destroy this advantage from the algorithm? And the good thing is that it's not, because the growth in the complexity of this error correction code is logarithmic. Okay, so it only gives you like a logarithmic overhead on this over this polynomial complexity of Shor algorithm. So the short answer is that, of course, if you want to go to larger numbers, you have to make better logical gates, which means you have to use bigger quantum error correcting codes if you use the same physical elements. Yes? You have some elementary physical gates, and you build from them logical gates with some reduced error. And you need to reduce this error more and more if you want to factor bigger and bigger numbers. But these quantum error correcting codes, they only grow like logarithmically with the size of the problem. So it does not kill you. But this is very relevant. You have to know how they grow to really show that you can reduce errors but still gain this advantage.
One more question. Is there any other problem than factorization in which we can expect the function supermassive faster?
Okay, so as I mentioned, people try a lot of things. This factoring is the most useful one. The others are a bit artificial. So, but of course, this is when I say Shor algorithm. It's not only Shor algorithm. It's a whole class of problems. Okay, the Shor algorithm also, apart from factoring, it has discrete logarithm problem in it because it's very similar. So actually, there is a whole class of problems which are similar to Shor algorithm, which can be translated to it. But if you ask for a qualitatively different algorithm with exponential speed up, which would be useful, then I don't know. But this is what people at this faculty should invent.
I agree. Okay, any more questions? We wrap up.
Can you speak once again?
I have a question of a completely different nature, like not related to quantum computing itself, not the science behind it, and actually I don't feel well prepared to talk about the science about it, the backstage of quantum computing, but what made the breakthrough of the classic computers was that they could be applied universally. We have one hardware to which we can upload roughly any algorithm, it will execute. We can switch it. The complex and flexible and universally available and useful. And is there any similar kind of approach or kind of work on quantum computers? So we could have one point, so to say.
Yes. So okay.
Which we can upload various algorithms. Because to me, all the thing looks like every quantum computer is built specifically for a particular algorithm or class of algorithms, which is exactly not what you would like to have with classic computers.
No, of course, yes. But this is just because we are in this infancy stage of quantum computing. So we just build dedicated devices. But in principle, you can think of all these schemes that I presented to you in a way that there are some qubits which encode data and some qubits that encode program. Okay? And these qubits that encode program, they determine what kind of gates will be acting on the other qubits. Okay? So in principle, you can construct such a universal scheme where you do not say that this is quantum computer for factoring and this is quantum computer for something different. So in principle, of course, yes. But this requires, again, some overhead in qubits and so on. So nobody does it at the moment because people fight just to build something. Okay? But in principle, it will be very similar to classical. You could have like the universal quantum computing. Maybe, I don't know, if an expert from more computing.
I'm a computer scientist more than a physicist, so basically the computers we have now already are universal. They are pretty of very low quality, unfortunately, but the Rigetti, IBM, Microsoft machines, they are already universal. You can run basically any algorithm you wish to run on it. The problem is the connectivity there. So you cannot run any kind of controlled node operation on these computers because those qubits are physically connected and there are limitations of what kind of operation you can perform them there efficiently. But nevertheless, through some clever techniques, you can run any general quantum algorithm on existing gate model computers. And the same is related to D-Wave. You can run basically any kind of algorithm that is suitable for D-Wave on D-Wave. There are some major problems with connectivity there, but they can be overcome pretty efficiently. Yeah, it's not easy, but it can be done, even now.
Any more questions?
Yeah.
So we've talked about scientific usages of this technology, but is there any business example of money being made with quantum computing already?
So I just mentioned this recommendation systems. Yes, this was a very business example. So unfortunately, it failed in the sense that it does not give exponential speed up. But I'm not sure if it failed completely, because in some sense it still gives a speed up which might be significant, even if it's not exponentially faster. So maybe this is not completely ruled out, this kind of application. But okay, I'm very bad in business applications, sorry. Maybe, okay, this is a...
Okay, there is one application that might be cleared up pretty quickly, which is quantum simulation. So that was the original idea by Feynman, that you can simulate the quantum mechanics using quantum mechanical devices. But quantum mechanics of some physical systems is pretty difficult, or chemical systems, for example, it's pretty difficult to run, to control, but you can control quantum computers. So there are now more and more companies are being established now that want to find new ways to simulate quantum states of matter and to somehow get some information about matter using quantum computers.
But I understand this was the question for business application.
That's business application. That's
business application is to sell something to scientists.
No. It's material discovery. You analyze materials. You can create new materials using that.
No, I agree.
So that's applicable in business.
Isn't even like a fast Fourier transformer, like a Fourier transformer, applicable in business in a sense?
It is, but as I mentioned, it's not that you get these results of this Fourier transform on your table. Yeah? That's the problem.
Okay.
If you had this quantum Fourier transform delivering you just the results of the Fourier transform, of course, you do apply it everywhere. But the problem is you just get some computation which you have to play with, and you don't have these results on your table. That's the problem. Okay. So you have to just use it inside some other problem which only requires some relations that are captured by a Fourier transform, but not the results of your Fourier transform, all the results.
Well, isn't that D-Wave was designed, this annealing algorithm, to solve some optimization problems?
Yep.
Some companies are using it.
Yes. But it's just, to show off that you are doing something with D-Wave and you sound nice, but it has not proved anything, as far as I know, that would not be possible to do on classical computing.
Yes, that's true. I even know about an example of optimization traffic in Beijing, which then subsequently was solved on classical PC, but this is also how the business works. People come with different products and there is a competition between different approaches.
Yes.
So quantum computers are, or this,
to
the extent D-Wave can be called a quantum computer. This annealing computer is already in the business cycle,
so it's kind of, I would say, it's kind of quantum-inspired computing device that solves in a non-standard way problems which might be difficult to come up with using standard classical approaches, but still they have not proved they go beyond capability of classical devices. Yes? But indeed, their formulation may sometimes give you a way to avoid, I don't know, local minima trapping in optimization in different way than you usually do in optimization algorithms you would use on classical computers. In this sense, they might be useful, valuable. I don't know. You know more.
I mean, using D-Wave is science fiction now. It's nice, it's interesting, but it's not really useful. And no company uses it, as far as I know, as far as I understand it, in practice. Just to explore the capacities of this machine and the capacities of general technology around it, developed around it.
Maybe just a matter of number of qubits in this machine.
And quality of this.
Yes, the noise.
But if you look at the business product cycle, something which is not very mathematical, from mathematics or not from physics, theoretical physics, but just from economy. There's always this early enthusiast or something like that phase where people are testing what is available technology and give feedback, etc., etc. And this is necessary really for development of the final product. So maybe we are just in that phase.
We should not lose enthusiasm.
So on the other hand, since quantum annealing algorithm has appeared, the optimization results, so to speak, have been, I mean, it has been a real progress in application. Not necessarily using D-Wave, I agree with that. Yes.
One comment I have that there are two machines, Fujitsu and Hitachi, which implement annealing. Basically, okay, they optimize the same problem as D-Wave, which is basically combinatorial ground state looking for classical Hamiltonian. But it uses different techniques. In case of Fujitsu, it is using FPGAs, and in case of Hitachi, it is a classical thermal annealing process. So there are new possibilities of use of solving combinatorial problems that can be kind of solved using D-Wave, and different other chips that are already available on the market.
Okay, thanks. Any more questions? One more.
So we have IBM and UF building quantum computers. You mentioned that Microsoft and Google is doing similar, so I'm curious what is their involvement. So Microsoft is developing this Q-Sharp, and it is currently, if I'm wrong, a platform for simulating quantum computations. And what are the other players in this game? You mentioned this.
Okay, so there are a couple of players here. One that is very interesting is Rigetti Computing. They are a relatively small company, recent startup that have an 18-qubit computer now, and they said that they will be able to build 128-qubit computer in 1 year. I don't know whether it is true.
It's also superconducting.
It is superconducting. Microsoft doesn't have any physical machine as far as we know. I mean, publicly it is not known that they have any kind of physical machines. And they want to build a topological qubit, which is science fiction now, which is completely, as far as I understand, impossible. Nobody knows how to do it.
It's a different way of implementing quantum error correction, but a very expensive way.
Apart of that, we have an Alibaba 11-qubit quantum computer in China. There is an Intel machine. So, as far as I know, there are like probably 6 or 7 different companies already having some chips running, to be considered to be quantum computers. Poor quality, but nevertheless quantum computers. Even Alibaba in China. No, there is no quantum computer in Europe. One is being built in Germany from the funded by the flagship project. But we don't know whether it will succeed. We don't know anything about it yet.
So maybe, because you mentioned about Rigetti, yes, and I also at the beginning said that we'll be learning how to write programs for quantum computers using Rigetti framework. So our 2 lectures in January and February next year will be dedicated to Forest, which is programming language, it's a programming framework developed by Rigetti. Last month, I was in California and I visited Rigetti's headquarters in Berkeley, and we are now discussing opportunities for collaboration, and it's possible that they will be officially supporting this group, and also some people from Rigetti from time to time can come here to give lectures as well. Okay, any more questions? No. So if no, then thanks once again to Rafał.
And I would like to thank Piotr for saying
Yes, thanks to Piotr for saying. As I said in the beginning, our next meeting will be in December, probably about 17th of December, so it will be still confirmed. And Piotr or another person from his group will tell us, or will give us introduction to programming quantum computers.
Quantum machine learning.
Quantum machine learning. Okay, so even better. Quantum machine learning. And yeah, so we'll still confirm the location. So we are considering different options, so just stay in touch on our Facebook group and just follow our announcements. So thank you once again for coming, and hope to see you again next time. Thanks.